All right, so on to the last on-badge GUI challenge, and I think this was probably my favorite.
Yeah, I think a lot of people will argue with you on that one. I saw some really interesting attempts at beating this one. There was 4 people stood around the badge with a button each, trying to get the timing right to solve this. It is possible to solve this just using the buttons. It's very difficult just because of the timing and the buttons, and there's no music.
Yeah, I think I really like these kinds of rhythm games. So even knowing there was a clever way of getting past this one, I actually enjoyed doing it the manual way. But I know others will, as you say, disagree. I think because of the refresh rate, it's a bit tough to see the moving arrows just on this video.
Yeah.
You can see them a little bit there, just scrolling up. But yeah, the idea is it is possible, obviously, to do it the manual way. It's tough, as you say, without the music. The kind of accuracy and timings are pretty tight, but yeah, I think it took maybe sort of half an hour or so of playing around to get through it the old-fashioned way.
That's probably the best I've ever done then. I'm glad that's being recorded. Yeah, and fun fact as well, I don't know if anybody figured out what song it is. But when Nathan put this together, he did have a song in mind. Yeah.
I was told it, but then in my mind, I was thinking of a different song. So I think it's supposed to be Is It Crazy Frog?
It's Crazy Frog, Axel F.
But then in my mind, I was thinking Baby Shark. So it didn't help me at all.
No, that's not going to help very much.
But for those who were a little bit more curious and maybe had their badge plugged in, what you will have noticed, if I just swap over to my Arduino monitor here, you'll see that there's some output here. This is the first challenge where we really get any output or any hints from the badge. And it says, oh, hey there. You can send up, down, left or right, UDLR to press the buttons. And you'll also notice the Fs that are appearing here. So if I turn auto scroll back on and we just follow this along, every time the challenge is failed, we get another F. That's our output. Now that's really useful, and what it means we can do is we can write a script that's going to solve this for us. If I swap into here, I have a script. You notice here that all it's looking for is that F to be sent out over serial. So that allows us to get our timing right. We have some variables a little bit further up that have the lead-in time and then the time for each step. It's a little bit of trial and error, but once you figure that out, it's actually pretty straightforward. So I'm going to run this script and we'll jump back over to the badge and we'll see if it can solve this challenge. We'll see how well it does. I'm going to swap our view here back over to the badge. You can see we've got the output here. So obviously when you connect over serial, the badge does restart. So if we go back to the badge, and I now navigate to the final challenge. Once we get in there, we should fail the challenge once. That's what's going to allow us to set our timing there. Our script is going to look out for the F. That means we failed. There you go, we failed once. And now, as you can see, the script is solving the challenges. And there you go. We got the happy dance. The challenge is now completed, and our LEDs have lit up along the side to indicate we have made progress.
Okay, so that's the end of the first group of challenges, the sort of on-badge GUI-based challenges. The next set are the more technical serial-based challenges. So how do we get to those? Simon, how do we get this set up?
So there's 2 ways you might have noticed this. So when you're going through challenges, once you finish them all, just run to the end of the corridor here. You get a hint as to where you could maybe look for some more. So if you connect over serial, there may be more. So that's a pretty solid hint. And more inquisitive people may have already had this plugged in and seen whether there's anything available over serial. So when I connect, the badge is going to restart. What you'll notice is even from the beginning, as it boots, it lets you know that there's things here and does warn you probably a little bit late at this point that connecting over serial will reboot the badge. So now if we switch back to the badge quickly and we open the challenge menu, we also get another message here. So if you'd like to tackle the more technical challenges, transmit a singular exclamation mark whilst on this screen. So I'm going to do that now. So we our exclamation mark in, we send it. And it just warns us, so we can switch to a slightly slower serial comms. Sometimes that does help. If the connection isn't great, maybe your cable isn't great, or you're having issues with clock speed and things, you're in a virtual machine, sometimes just slowing things down a bit can help. And then a little bit of an introduction. So this is the beginning of a series of technical challenges that are now carried out exclusively over serial. So we turn off the display. So now back on the badge, the display itself has been disabled. We do this because we want to try and save a little bit of your power. And to return back to actually being the GUI based badge again, you just need to power cycle it. Disconnecting from serial will usually do that anyway. So for now, we're given a couple of commands and it seems that we can read files. So we'll give that a go. So we use R and file name. So it's asking us to read .challenges/intro. I think I typed something wrong there.
Missed an R, I think.
Did I? Yes, I did. There you go. Computers are hard. There you go. Congratulations on reading your first file over serial. So this is largely an introduction to how the file system that we're interacting with works. So as we work through these challenges, we're going to layer on more techniques. So we've read a file and it's not encrypted, but all future files will be from this point on. To read encrypted files, first we need to set the key. Using a new command now, we've got care and then the password. Once we've entered our key, we can then try and read the file as usual. So just to demonstrate that, if we try and read encryption 101, it's like having somebody over your shoulder. Typing is hard. It's garbled. If we set our password, so care, password, and now try and read the file, we get some nice output. So now we've set the password and we can read the file. So we read challenges encryption 101. I failed to set the password. That's much better. We get some more output. Just we'll start at the beginning, a very good place to start. And what looks like something a little bit garbled, and then instructions to read the next file. The next file is encryption 102. Now, we could try and just read encryption 102, but of course it's not going to be that easy. We need a password. this text here does look like it's possibly encrypted. The challenge here is figuring out maybe what it might be. So there's a few ways of doing this. There's also some obvious schemes I like to try first. So something like this, where we can see we've got some repeating characters, we've got some things. We can take that and go back to our rusty tool from earlier, CyberChef. So I've just copied the text out of the terminal we had and put it into the input window of the output window here. And the answer here is it's XOR encryption, and we don't know the key, but CyberChef has a very handy brute force function. Now, in this instance, it's a single byte key. It's very easy to brute force, and we can just drop this recipe in and take a look and see if any of these start to make sense. When we find the right key, one of them will look something like readable text. And there it is.
Oh,
the key is 58. So it's not quite right. Obviously, the T here has been not quite decrypted, but it's good enough. We can read what it is. So it's the quick brown fox jumps over the lazily encrypted password. It's foxes. So we can take that now back into our terminal. Try setting it as a key and see if that'll let us read the next file. So as before, K, and then the password, foxes. Let's try reading encryption 102.
Looks good.
And here again, we've got some more output. Of course, CyberChef has more tools available within it. And if you ever run into a problem like this, and you're not sure quite what it is that you're looking at, one of the really, really cool features is this magic recipe. So we drag it across much like any of the others. And what it'll try to do is run through the rest and try and find something that makes sense. And we're going to tick intensive mode, which asks it to go in, try a little bit harder. And you'll notice straight away, the first option is exactly what we found before. So sometimes, if you're not sure, using this magic function can be really, really useful.
All right. So encryption 102, what have we got next?
Yep. So if we take the password from when we decrypted this this string here, so the password, of course, was foxes, and set it as the key, we can now read challenges encryption 102. Excellent. So we can now read the content of a new file. And there's a little comment about the previous challenge. Obviously, XOR of a single byte is a really bad way of doing things. Very common in these low power situations, but as we've proven, not awesome. So the password for the next file is stored within the EEPROM on the chip. So this is the memory that's part of the badge that you've got there. And we have a function here that will help us read from EEPROM. So we can use the character E. That's an uppercase E, followed by the address that we want to read, and it'll return the value at that address. Now, the important part to note here is that we need to send it as a raw byte. So at this point, we're going to have to park the Arduino serial monitor because we can't send raw bytes in here. It's unfortunate, but we'll need to pull something else out of the sort of toolbox. So the way I've solved this is I've written a little Python script. So if I this, so the top half of this script isn't super important. I've written a little bit of a Gradle that will help me write solutions to these challenges. And all it does is it connects over serial. It waits for the user, you, to hit enter once you're on the challenges menu. Because once we connect over serial, the badge will restart and you don't want your script to run early. So it waits, we hit enter or return. It sends the exclamation mark that drops us into the challenge mode. And then all it's doing is just dumping the first 255 bytes of memory. That's all it does. It loops through and it just dumps out the values. So if we run that now, we get an error because I didn't close the serial console.
Love it.
There we go. So navigate to the challenges menu. So my badge is restarted. I'm in the challenge menu now. I hit return. As you can see, it's just looped through and it's dumped some values out of memory. Now, those more familiar with Hex may notice that these characters here look a lot like they may map to ASCII values. So we copy these and go back to our trusty tool, CyberChef. Now, once again, here's one I prepared earlier. I've copied these in and I've separated the values out. Now, as we saw in the last one, the CyberChef magic does work, and we can just click here if we'd like. CyberChef itself has worked out that these are, in fact, values. We can click on this here. It brings in the from hex, and hey, look, we have a password.
Simple as that.
CyberChef really does make things easy. So what we'll do is we will try and access the next file using that password. Okay, so if we take the password we've just got there, which was, of course, EEPROM password, we should now be able to read EEPROM 101. And look at that, we now have some output. So we've now figured out how to read from EEPROM. So our next challenge here, obviously, is going to be how to write to it. So once again, we've got a handy function here, which is a lowercase e. And with this, we use the address where we'd like to write the data, and then what data we'd like to write. And once again, both of these have to be a raw byte. So here's a handy example. So if you wanted to write to this address, this value, here's the command you would use. So to get the password for the next file, we need to reverse the first 15 bytes, which is where the password we've just got is stored, so that they now read Drausap Morpi, or EEPROM password backwards. And our next file is going to be EEPROM 102. So once again, we're going to drop to Python. You can do this using other tools. You just need the ability to send raw bytes over the wire, which we can't do in this terminal. So I'm going to switch back to a command prompt here. And once again, I have a handy script. You'll notice the cradle at the top is exactly the same. It's just waiting for the key press. And then there are definitely more elegant ways of solving this, but I did it the lazy way. You could do this with a loop, but this works. So all we're doing is we're going through the first 15 bytes of memory and we're writing the password we got earlier backwards. So if we run this now, again, it'll ask me to navigate to the challenges menu. Press return to continue. As you can see, we get some new output. We get the password is I can write. So if we Jump back over to the serial monitor. And we try using that as our new password. So we've got I can write. And we need to access the file EEPROM 102. So that's our challenges EEPROM 102. Excellent. So this file is a little tricky to read on the stream. I appreciate that. I'm going to try and do my best, but I'll also read it to you. Excellent. So now we can read files. We can read and write to memory. And up until now, we've been using the R command, so capital R, which takes a file name as an argument. Now, internally, so this is a custom file system and command set that was written by one of the team here. This just performs a lookup to convert the file name into a node ID and then looks for the file matching that ID. During this process and the conversion to a node ID, the file attributes are checked. And if you're not supposed to access the file, for example, it's hidden, then it will not let you access the file. Now, of course, there's always a way around this. So we have two new commands. We've got F and R. That's a lowercase r, which allow us to do these steps manually. So F can take a file name and it will return the node ID and the file attributes. And R, lowercase r, can read the file using its node ID. So our challenge here is that we need to read the file challenges.hidden. And the key is hidden backwards. So there's a little bit of an explanation here around the file attributes. So you can use this command to have a look at the other files and have a poke around the file system. But the one we really care about here is challenges.hidden. So once again, we're going to have to send these values as raw bytes. So I'm going to drop back to Python. You can solve this other ways. I saw people working on this using putty and similar tools. Anything where you can send a raw byte will work. I just chose to use Python. So I'm going to jump back into my terminal. And we'll have a little look at the script. So notice the same cradle at the top. But what we are doing this time is you'll notice when you connect over serial, the badge will let you know that you can switch to the slower serial communications. So I was having some timing issues with this one, and I sent the uppercase B, which just lowers the baud rate of the serial communications. This does still work without it. It was just I was running a virtual machine and the timing was a little bit out, so I just slowed it down to make it a little bit more consistent for me. And then into the actual challenge. So all we're doing here is we're setting the key. Here's our K command and the password. We're using the F challenges hidden to get the file attributes. And then we're going to use the lowercase r and the file node as a raw byte again to get the contents. So if we try running that now, it'll say no because I didn't close my serial monitor. Jumping between windows is hard. There we go. My badge restarts. I jump into the challenge menu again. I hit enter. And there we go. So once this finishes typing, I'll scroll up a little bit and show some of what happened here. So in the script, you could see that we set the key. Here's the output from that command. We've got a 5 here. This is the node ID that was returned when we did the lookup.
Right.
And then reading that file at that node ID, here's our output. So this takes us into the final challenge. as it says, we've now mastered reading and writing to memory. We can access files directly by node ID. And now, what we're going to have to try and do is read an encrypted file. But the file system hasn't been told it's encrypted. Remember the file attributes from the previous challenge? One of those was whether the file was encrypted or not. So if we take another look at these, you can see that we have the badge FS attribute encrypted. That is not set on the file we're going to try and read. So we have a file name, challenges.encryption, and we have a password. But when we try and access the file, even if we set the key, because the file system was not told it's encrypted, it's not even going to try and decrypt it. Why would it? But that's okay, because, hey, we're going to give you the details of the encryption scheme. Almost. We're giving you the compiled AVR machine code for the encryption scheme. Now, we've provided two functions here. We've got the sdcrypt and the sdderive key. So these two calls are what are used to decrypt the files. As you can see down here, so file reads are performed by first calling sdderive key with the password to get the encryption key. And then sdcrypt contains the routine to decrypt the file. So the challenge here is going to take us away from the badge and becomes a reverse engineering challenge. Now, this is a very long process. And we're not going to go through this step by step here. What we can do, if there is enough interest and people ask for this, we can create a longer blog post to talk around the details of how this reverse engineering works and how to find the output in the end of this.
Well, hopefully this is enough to point people. I mean, this is the final challenge, right?
Yeah.
And hopefully this is enough clues to point you in the right direction or to understand how to solve the final challenge. But yes, to go through every step, sort of line by line, if you like, is much more than this video was intended for. But maybe something like a blog post, if people are interested, we could certainly look at sorting something out for that.
Yeah, absolutely.
All right. And that's the final one. And what happens when you complete the final one?
So once you've managed to do the reverse engineering there and you read the file, what you'll find is that the final file here contains some quite cool and interesting stuff. So scroll back up here. So first off, congratulations. That last challenge in particular is tough. For those who do go and solve it, well done. Second, of course, given the buttons that are available on there had to be a secret code. So here's the code for enabling the super user mod. Now, it doesn't enable anything particularly crazy, but it does let you customize some extra features of the badge and do some cool things. And the other thing we've included here is the pinout. So for those who like to play with hardware or just want to see what else they can make the badge do, here is the pinout should you wish to try and write your own firmware for these badges. We have some information around the clock speed of the chips, and just mentioning that obviously the exposed pins down the left do have everything you need to program these over ISP. I will say that they are also configured to allow programming over USB as well. It's a little bit less scary. So BadgeFS, the file system we've been interacting with through these challenges, there's some information about that in here too. And once again, so I know we spoke at the event with some people around this, around the reset on the badges. The EEPROM.bin is what allowed that. And this is the golden copy of the memory. And it is encrypted. Now, you can potentially crack it. We've had a look at the encryption scheme on the badges. Be really curious to see if people do that. But other than that, some useful information in here to enable you to go and do some cool and interesting things with these badges. And we're really excited to see what people do with them.
All right. We hope you had fun with these challenges. We certainly had fun designing them. If you're still stuck, please reach out. We'll do our best to help. But that's it for today. Thanks.